So yes, as Tom said, I'm going to be talking about Venus tonight. I just want to get a quick check here first. You know, who here has been who has seen the planet Venus in the night sky? Right. Okay. Good. You know, just so I can check who hasn't. Okay. No, that's right. I mean, it's a very obvious thing in the sky, especially the last few months. I mean, it's the brightest object in the sky after the sun, which is hard to miss, and the moon, which in this photo here, also very hard to miss. And then the next brightest thing in the sky is Venus. And especially lately in the western sky, we see in the evening, there's been a series of conjunctions with Jupiter. And this photo was actually taken about a week ago, not by me, during those conjunctions. And in the meantime, unfortunately, it's been snowing here. But Venus has now come very close to the Pleiades, and so definitely on your way out tonight, take a look at Venus again, and try to see if you can pick out the Seven Sisters or Subaru as well nearby. And as I said, Venus is very, very bright. Part of the reason for this is that, as you may have noticed in the first slide, it's completely covered in clouds. Those clouds tend to reflect about 70% of the sunlight that comes in, and so what we see is a very bright reflection of that sunlight. In fact, it's so bright that, and this has actually been documented, UFO reports are seen to increase at times when Venus is visible in the evening sky. And in fact, even people who know better are sometimes fooled. You may have heard the true story about a former U.S. Naval Academy and U.S. President Jimmy Carter. Now, any U.S. Air Force Academy or Navy vets here? There we go, Bill. Okay, it's just the one. Now, as I understand it, Bill, at least once upon a time, before GPS became so prevalent, celestial navigation was a big part of the USAF and U.S. Naval Academy curriculum. And so what that involves is being able to identify where you are by studying the sky. And you're not going to be able to do that without knowing the difference between a star field and a planet, or a planet and a UFO, or some other, or even an aircraft. And so Jimmy Carter had taken these courses, and so, quote, should have known better. But I think we can cut him a little slack, because I was reading up on him, on his history a little bit, and I didn't realize, it shows my age, I guess. I didn't realize he was in the Naval Academy, but when he was on duty, apparently he spent most of his on-duty years in a submarine. So it's kind of hard to see the stars from there, so I can cut him a little slack. He probably got a little bit rusty. And so it's probably not surprising that the first known recorded observation of a planet is of Venus, or the first known astronomical observation, a planet, star, or anything, is actually Venus. And it's a clay tablet, the observations of which date to the 17th century BC. The tablet itself is about 1,000 years more recent. And so, I mean, if as you all have, if you've seen Venus and you notice, I mean, just how unmistakable it is, how unmissable it is, you can almost imagine, even prehistoric humans, looking up and noticing that, here's an object here that's doing something that, everything else. You get the sun, that's important. The moon, that's a big object too. We can't miss that. But now here's this thing that looks like a star. All these other stars we see up there, but it's doing something a little bit different. What is it that's so different about this object? And today we have computers and the space shuttle. Well, it's not the space shuttle. The Mayans also were very keen on Venus. They had a special place in their heart for Venus. In fact, they called it Kukulkan, which was the god that they associated with the planet. And there are many appearances of Venus that were recorded in the Dresden Codex, which is just a series of stone books that were discovered. And pretty much the only reason I'm talking about this today is, everybody knows, the Mayans predicted the end of the world at the end of this year, partly because of their cycle of the calendar and the apparitions of Venus, but no, really what they saw was Y2K, and I thought we had all the Y2K stuff done 12 years ago, but now the Mayan Y2K problem is going to strike us. But since the Mayans didn't have computers, I think we're safe. And so another thing about Venus is that observations of Venus played a very central role in one of the biggest philosophical shifts of thinking in Western civilization. And that is the conversion of a Ptolemaic or Earth-centered worldview to a heliocentric view of the solar system. Now, at the time, it was of the universe, but we'll try to simplify things for now. Now, Ptolemy was around about the 1st century AD, and made a number of observations of the motions of the planets, and this was his best guess describing what he saw. He figured, okay, Earth is at the center, all the planets go around the Earth, including the sun, including the moon, but that didn't quite get it. You know, sometimes the planets kind of did this little dance in the sky where they went back against themselves for a few weeks or months. So he had to explain that somehow, and so he added these things called epicycles, and it seemed to work. I mean, it seemed to do a decent job of predicting where the planets were going to be in the sky, but 1,500 years later, 1,400 years later, it became clear that this wasn't cutting it anymore. I mean, this model wasn't doing a very good job of predicting the position of the planets unless you made things far more complicated than this simple model appears. So Nicholas Copernicus realized that you simplify things quite a bit if you put the sun at the center of the solar system and you had all the planets, Mercury, Venus, Earth and the Moon, Mars, Jupiter and Saturn and the stars, and you had all those go around the sun. Now, unfortunately, this didn't do a much better job of predicting where the planets were going to be, but it was simpler. It gave in the gut of a number of scientists at the time, it seemed more right, and so attempts were made to try to identify which of these was accurate. This brings us to a nice quote that I sometimes hear from Richard Feynman that gives a good, it's partially paraphrased here, and then this is the tail end of the quote. That gives a good picture of how science really works. I mean, you all learned the scientific method in school. Well, that's not really how science works. It's closer to this. You actually go and see something, go and sense something. You see it, touch it, taste it, feel it, whatever. Go observe something, make a guess to explain what it is that you've observed, and then go make some predictions based on the guess. What else will that tell you about what's going on? And then compare those predictions with the new observations. And then that leads to the rest of the Feynman quote, and it doesn't matter how cute your model is. If it doesn't match the observations, it's wrong. And either your model is wrong or your observations are wrong. And science is a constant going around this cycle. And I'm going to come back. I'm not going to bring this slide up anymore, but I'm going to bring it back verbally a number of times through the talk. Now, as I said, right now we're talking about the role of Venus in identifying the difference between the Ptolemaic and Copernican view of the solar system. Now, Galileo saw the Copernicus model, and again, he felt in his gut, this is right. This is going to explain how the solar system really works. And then he learned about the invention of the telescope by Hans Lippershey in what's now the Netherlands in it was discovered in 1608. He started building one in 1609. And actually, I'm going to stop because this is actually old curmudgeonly Galileo. At the time of these observations, this is actually the Galileo we're talking about, who was observing the phases, who was observing Venus with the telescope, observing the skies with the telescope, building his own telescope. This portrait is dated to sometime during his years at the Padua Observatory, which is when he had made a number of his observations. So I'm going to leave younger Galileo on the screen for the rest of this slide. So he built the telescope and observed Jupiter, and the first thing he noticed was, well, first of all, Jupiter wasn't just a dot. It actually had a shape. It actually had a disk. And he also discovered that it had moons. And in combination, after viewing these for several nights, he realized that both Jupiter and the moons were shining by light reflected by the sun. They weren't generating their own light. So this told him two things that I'm going to get to in just a moment. The conclusion of those two things is that he knew that in this telescope, he had a tool that he thought could settle for once and for all this dispute between geocentrism or heliocentrism, the Ptolemaic model versus the Copernican model, and he is mostly right. To understand this, we'll look back at the two models, but we're going to zoom in on the inner solar system here in the next slide. Oops, if I hit the right button, we will. Now, in Ptolemy's version of the solar system, you had the sun. It went around the Earth once a day. Now, observing Mercury and Venus over the years, you can see, I mean, everybody knew since the Greeks, and probably even before, well, actually, as I said, as I showed in my early slide, even the Assyrians knew Venus did not ever get very far away from the sun. Now, Ptolemy solved this by saying, all right, well, Mercury and Venus, sure, they're going to run around an epicycle just like the outer planets, but this epicycle is going to be tied to the location of the sun. So Venus always stays pretty close to the sun. You're never going to see Venus over here while the sun is over here. Copernicus, on the other hand, with the sun at the center of the solar system and everything happily going around, had the situation where you could sometimes have Earth on one side of the sun, and Venus on the other. Now this is significant because of the illumination. If everything's shining by reflected sunlight, if Venus is always between you and the sun, its illuminated side is mostly pointing away from you. So when you look at Venus, you're always going to see a crescent phase. Whereas if you have this situation, if you're looking at Venus and it is in this part of its orbit relative to the Earth, it's going to look almost full. It's going to go through all the phases, the same phases that the moon goes through. So Galileo knew, if I just observe Venus for long enough, over a full synodic period, I'll be able to tell whether or not Venus is going around the sun or whether Venus is going around the Earth. And sure enough, this is what he ended up seeing. He saw that Venus did indeed go through a full suite of phases. When it's on the far side of the sun, it was full. When it comes around on the near side, it's a crescent. And this was able to repeat itself. He thought, I've got it. But unfortunately, what Galileo didn't realize is that it's difficult to overturn 1,000 years of accumulated thought and wisdom. Even if you're right, it's difficult. And we've actually had an example of this in very recent memory. If you remember in the news this summer, Large Hadron Collider reported observations of neutrinos traveling faster than light. The problem with that is, Einstein had been around for, his theories have been around for 100 years, have been tested over and over again. Remember, what do we do in science? We make observations, we make a prediction, make a guess based on those observations, Einstein's theory of special and general relativity, and we make predictions based on that guess, based on that theory. And these guesses were tested over and over again. They were tested observations of starlight during a solar eclipse, observations of clocks in the space shuttle. And Einstein's theories came up roses every time. And now all of a sudden we have this new observation that says, wait, something can go faster than the speed of light, even though everything that Einstein came up with said this was impossible. So most of the scientific community was understandably skeptical. Because you had this one observation that said Einstein was wrong, and you had a number of other observations that said he was right. How do we solve this? As it turns out, we found out that there were errors in the observations, and fortunately the establishment the 100 years of progress that we had in science was right, and we didn't have to go and throw out 100 years of physics. But that was the dilemma faced by scientists and philosophers around about the time of Galileo. They were looking at the possibility of throwing out 1,000 years of what they thought they knew. So they were, a number of them were reluctant to do this. Second reason a number of them were reluctant to do this is because not all of the observations fit what Copernicus said should happen. Tycho Brahe, actually before Galileo's observations were made, now, another part of science, remember, I said we do a lot of observations and we make a lot of guesses. And then we compare those guesses. And really what it comes down to, scientists tend to shake out into two flavors of scientists. They're the ones that are really good at the observations, and they're the ones that are really good at guessing. And then a very few are really good at both. Tycho Brahe was really good at observations. He's easily the best observational astronomer since ancient times, and possibly the best we've had ever. He was not so good at guessing as it turns out, but he could observe. He observed the motions of all the planets and measured the locations of many stars. And in fact, his observations of the planet eventually were so good that they were able to lead to the Kepler's laws of physics, Kepler's laws of planetary motion, which we'll talk about in a little bit. But what he recognized in observing the stars is that they didn't move. They did not. They were in the same place all the time. And the problem with that is something called parallax. Parallax is very simple. It's the apparent motion of something based on a change in perspective. And so one way to get a feel for that is if you just hold your hand out in front of you and you kind of close your right eye and you notice where your finger is off in the distance. And now switch eyes. You start with your right eye closed, close your left eye and open your right eye, and notice how your finger moves relative to what's more distant. That's parallax. And so all that's happening there is your perspective has changed. And so you're starting here, you look, and it's in line with that. Now you're in this part of the orbit, and now it's in line with something else. If the Earth was going around the sun, everybody knew you should be able to see a parallax, and we didn't. Couldn't observe it. And so Tycho's solution was fine. Copernicus seems to get everything right about retrograde motion and the motion of the planets. And so I'm going to have all the planets go around the sun, which is what he's showing with these rings. But then I'm going to have the sun go around the Earth, which is the dark dot in the center. Now it seems a little silly, but it fit. I mean, as far as he could tell, this was the best fit to the observations that we had at the time. And upon further inspection, what you find is that really the only difference between Copernicus' model as it's drawn here and Tycho's model as it's drawn here is a frame of reference. They're identical, except on one you say, I'm on the Earth and everything happens according to me being stationed on the Earth. The other one is, I'm standing on the Earth, but the sun is stationary and everything happens going around the sun. The way to solve this is to observe stellar parallax. Problem is, stars really are really far away. And to give you an idea, Pikes Peak is about 130 kilometers, about 80 miles away as the crow flies. So the nearest star to the Earth has a stellar parallax. It's going to move in the sky over the course of 6 months, 2/3 of an arc second. We don't need to know what an arc second is. What that is equivalent to is, there's a foot ruler. It's equivalent to moving 2 feet if I'm standing here on the roof of LASP. Obviously, you're not going to see me if I'm in the building. So there's 1 foot, 2 feet. So if I were going to place you, I'm going to tell you, go to the summit of Pikes Peak, and I want you to tell me whether I'm standing here or here. It's really hard to do, even if you had today's telescopes.
That would be so hard.
It's very difficult. Poor Tycho Brahe didn't stand a chance. It wasn't actually until 1680. Nope. Sorry. Next slide. It wasn't until 1838 before you could actually observe a stellar parallax that small. However, in the meantime, Isaac Newton, who was born approximately the day Galileo died, discovered and developed the laws of gravitation. He published these about 100 years after Tycho Brahe's model. And what these suggested was that there is actually a way to indicate whether this is more likely or this is more likely. And the way that was indicated is whichever object, whether it was the sun or the Earth, whichever was more massive, that was more likely to be the thing at the center of the solar system, because you had force equals mass times acceleration. The forces were the same, and so If you had a bigger mass, you had a smaller acceleration, you didn't move much. If you had a smaller mass, you had a bigger acceleration, you did. But nobody knew how far away the sun was, and so we couldn't figure out how big the sun was. So it became a key point of astronomy to figure out what is the distance from the Earth to the sun. Now, there's a ton of equations on here, and I thought I was very clever when I went through this, but I realized I'd probably bore you with a lot of it. So I'm going to concentrate only on this last bit. What this comes down to are two things. We start with Newton's law of gravitation and Newton's second law. It's force equals ma. Force equals mass times acceleration. And we do a lot of algebra. And what we find is we can show that the mass of the sun relative to the Earth is equal to a bunch of things we know and only one thing we don't. Okay, 4 pi squared, these are just numbers, no problem. G, this is the acceleration due to gravity at the surface of the Earth. I mean, Galileo had been measuring that, so we've known this. Again, we're talking, this is the time of Newton and later, so we've known this for at least 100 years. The radius of the Earth, well, the ancient Greeks, I mean, Aristarchus had measured the radius of the Earth in the 3rd century BC, I think it was. So we had known the radius of the Earth pretty well for a long time. And the period of the Earth, in other words, the length of the year, again, that's something we had known, that's something even the Druids were trying to measure, and by the time we're in the 17th century, we had a pretty good grasp of the length of the year. Now, we don't know what the mass of the Earth is, but remember, all we needed to know was what the relative mass was. You know, was the mass of the sun much more than the mass of the Earth, or the other way around, or were they about the same? And if we can measure the distance between the Earth and the sun, we can identify that. Now, the problem is, at the time, the best guesses for the distance to the sun were widely varied. From about 300 times the radius of the Earth to about 10,000 times the radius of the Earth. And the problem is, that left a huge range of possibilities for this mass ratio. So what we needed to do, we being astronomers, many years before I was born, was to identify, well, what is that number equal to? And we could answer whether or not everything went around the sun or everything went around the Earth. Now, it's very easy to determine the relative distances. This has been done for some time. All you have to do is observe Venus and see when it gets its farthest from the sun, and you actually can work out this simple trigonometry, and you find that, well, Venus never gets more than about 47 degrees from the sun in our sky, which indicates that distance from the sun to Venus is about 7/10 of the distance from the Earth to Venus. But again, we don't know these in actual units, and so this doesn't quite help us. But it gives us the first step in the measuring of the astronomical unit as determined by an observation of a transit, which is determined by Edmund Halley, the same Halley of the comet fame, which is one of the reasons why I alluded to that in the abstract. What he realized is that if you observed a transit of a planet, you could measure this distance between the Earth and the sun. And the way you did this was the following. So you were at home at position A, and you sent your friend to the other side of the world, not because you didn't like him, but because you thought he could help you. And so ideally you'd send him to the far, to somewhere that's very far away, but it makes the drawing a little bit easier if I only send him to roughly the equator. Since we know what the radius of the Earth is, we can actually measure this distance pretty accurately as long as we know where we are, and that's a whole other story. And so we know the distance between the Earth and the sun is some value d, and we just measured what the relative distances are. Again, Venus to the sun was about 0.72, and this 0.28 is the rest. And now if we observe a transit of Venus as it crosses the sun from these two places, we see that person A, she sees the sun, she sees the planet Venus cross the sun very low on the disk, whereas person B sees it cross near the equator. Fill out those triangles, and the difference between the positions of those two transit crossings is equal to an observable angle. You can actually measure this angle between where person A sees the planet go across and where person B does. And if you do that, with a little bit of trigonometry, which I'm not going to go through, and some more algebra, you can actually measure the distance between the Earth and the Sun in terms of this supposedly known distance between you and your friend. Now, what Halley realized is that if the distance is big enough, this angle is going to be very, very small, and it's going to be very hard to measure precisely. However, a transit of Venus actually takes 6 or 7 hours, depending on where you are located. And so what he realized is that you could probably get better precision if you measured the time it took to observe the transit, because if person B was looking at it down here at the lower part of the sun, notice that Venus shows up here first, and then it shows up here, and then it disappears off the limb here before it disappears off the limb as seen by person B. And if you compare the two times, that was the same as measuring this angle, but you could do it with better precision. And so he realized that, in 1761, there was going to be another transit. That was going to be the next transit of Venus. This is several decades off, as from his vantage point. And so he suggested, well, why don't we just send astronomers and observers all over the world, somewhere that the transit can be observed, so that the entire transit can be observed in the white areas. Part of it can be observed in the gray, and none of it in the dark gray. To go observe the transit of Venus, compare our results. Unfortunately, Europe is up here, and you had to send people partway around the world to India, China, the Philippines, Indonesia. Unfortunately, in 1761, there's a bit of a war going on. Here in Americas, we call it the French and Indian War, and the rest of the world it was called the 7 Years' War. And this was at a time when there were a lot of fast ships on the oceans with big guns. And even if you put someone on a ship and said, "Hey, I'm a scientist, please don't shoot," they were unlikely to hear you at the distance that, they were more likely to be close enough to be hit by a cannon before you could say, "Please don't shoot, I'm a scientist." And so most of the attempts that were made in 1761 met with failure as a result. However, there was one fellow observing up here in St. Petersburg, Russia, a fellow by the name of Mikhail Lomonosov, who was able to observe the transit of Venus. And he made a very key observation at the time. When he saw the planet approach the disk of the sun, he noticed that a ring of light went completely around the disk. And he was smart enough to realize that the only way this was possible was if Venus had an atmosphere. If Venus was just a solid body, you wouldn't see this diffraction all the way around the planet. This is the first time that any planet in the solar system other than the Earth was recognized to have an atmosphere. Unfortunately, Russia was a bit of a backwater at the time, or at least was perceived as such by Western Europe, and nobody in Europe really was aware of these observations. And it wasn't until the mid-1800s before another Western European astronomer was able to make a similar observation and a similar conclusion. Fortunately, transits of Venus come in pairs. And the next one came around in 1769, and this time, the war was over. And so all sorts of nations of Europe sent their scientists on missions, several year, 3, 4, 5-year missions to explore, for scientific purposes, explore strange new worlds, new civilizations, and uncharted frontiers. These were the voyages of almost. Actually, folks like Captain Cook, who observed the transit of Venus from Tahiti. Not a bad place for a vacation. Now, the reason for that is I'm convinced, I haven't seen this admitted to anywhere, but I'm convinced that Captain Cook and his mission to observe the transit of Venus provided provided a model for for Star Trek and Captain Kirk and the Enterprise, and the missions were very similar. As an interesting exploration and scientific combined, and at times military endeavor. Now, the reason for all of this is, as some of you may know, there's the last transit of Venus, which anybody alive here today is likely to see. You guys maybe might be around for the next one, although I wouldn't bet on it. It's a long time off. They don't happen very frequently. The next one is going to happen in about 105 years in 2117. How old are you going to be 2117? 115. Yeah. Good luck. I'm rooting for you, but it'll be tough. But we can see most of the transit here from Denver, and so I just want to show this. Denver's up here. The first contact, when the edge of Venus first reaches the disk of the sun, happens about 4 o'clock local time. The sun's going to be about 47 degrees above the horizon. Second contact is when the entire planet's disk is in front of the sun. That happens about 15 minutes later. And the center of the transit happens very close to sunset. I'm not sure. I think it depends where you are, whether or not the sun will be behind the mountains at this point. So you'll be able to see the first half of the transit from here. If you want to see the whole transit, you'll have to go to Alaska or maybe Hawaii, most places in the Pacific, Japan, or the Arctic. Now, the other thing about transits, observations of transits today we're still learning more about our place in the solar system, our place in the universe by observing transits. The Kepler mission, named after the same Kepler I mentioned before of planetary LASP fame, is actually operated here at LASP. And what it does is it spends its whole time staring at thousands of stars and just waiting for a planet to pass by and transit, which changes the light curve. It actually blocks a little bit of the sunlight. And we have actually, the point of this mission is to try to figure out, well, how many planets are there in our galaxy? And Kepler is well on its way to coming up with a decent answer to that question. Another spacecraft that we have here that is operated here at LASP, which is also developed here at LASP, is the SOURCE mission, and this has the job. It's very similar to Kepler, except it is staring just at the sun all the time, and its purpose is to understand how the sun varies with time. So, if anybody you get into an argument with a global warming skeptic on the street, and they say, solar variations are causing all of the global warming that we see, and nobody's observing this. Nobody wants to observe this because it doesn't fit the picture. It doesn't fit the global warming picture that we've developed. Well, yes, we are here at LASP even. The SOURCE spacecraft is observing the sun all the time and trying to characterize the variations in sunlight. And in 2004, because it's staring at the sun the whole time and Venus happened to pass by, it also managed to catch the transit of Venus. And this is interesting. This is even further interesting because Venus is a planet that we know very well. We've studied it a lot more carefully than these other planets that Kepler is observing, well, because we've been here, and it's going to be a long time before we go to the planets that Kepler is observing. And so if we can study light curves like this, where we can observe the sun, which we've been studying for many years, and we can observe Venus, which we've been studying for many years, grasp as to what the changes that we see in this light curve are, we can actually use it a little bit down the line to understand even more about these planets that we're observing around other stars. And so, coming back a little bit, trying to bring us into the space age a little bit, so why do we study Venus? In addition to the points that I've made so far, this is looking again at more recent observation. Now, this is kind of a historical point, but 50 years ago this summer, the first successful scientific interplanetary probe was launched from the Earth to Venus. There had been a couple of unsuccessful scientific probes, and there was one, I think just one, I might be off, but there was another probe that basically demonstrated, yes, we can get there. I think that was one of the early Soviet missions. But there was no science return other than, yes, we got here. So this was the first, and so what we're looking at is this summer we're celebrating 50 years of planetary exploration, which I think is pretty cool. But what Mariner did is it confirmed that there was a very high surface temperature on Venus, which up to this time there was some question about. There was some indications that it was a high surface temperature. There were other possible explanations. But what Carl Sagan had shown just a few years before this was that if there is a strong greenhouse effect due to carbon dioxide and water vapor in the atmosphere of Venus, then the planet Venus would have a very high surface temperature, and then sure enough, Mariner came around and confirmed this. And what this showed us was that it basically showed us the power of the greenhouse effect. That the greenhouse effect had been known since the 19th century, but this was an example of the greenhouse effect causing hundreds of degrees of warming, which showed that hey, maybe it's not such a good idea to be putting so much CO2 into our own atmosphere, because if we put enough in, we could eventually end up in a pretty bad situation. And so right about this time is when global warming studies gained a little bit more focus. Another thing that we've learned about Earth by studying Venus has to do with the ozone hole. Some of the early missions to Venus were able to measure atmospheric components, and they noticed that there was chlorine in the atmosphere. And so, again, what do we do in science? We make observations, we make guesses to explain what we see. They make new predictions, we make more observations. So, okay, we see chlorine, all right, well, what's it doing there? What's the result? What happens if we have a lot of chemistry going on in the upper atmosphere and we have chlorine involved? Well, some Venus scientists went to work on this problem. In the meantime, here on Earth, we realized that there were things called chlorofluorocarbons, which we were producing, coolants and propellants. We realized that those could reach the stratosphere, and the only way to get rid of them was to destroy them photochemically in the upper atmosphere. And then shortly after that, ozone depletion was beginning to be noticed over Antarctica. Basically, these three disparate ideas were kind of put together by Venus scientists and Earth scientists who realized that there was a common thread here. Said, well, we've been incorporating chlorine into our photochemical models for Venus. Why don't we just take those same models, kind of tweak them a little bit, so we were explaining Earth instead of Venus, change the components of the atmosphere, change the amount of sunlight we get, and all these other things, and let's see what happens. And what they found was that, sure enough, on Earth, if you had free chlorines in the stratosphere due to breaking up chlorofluorocarbons, you could destroy the ozone layer pretty darn efficiently. And sure enough, over time, we started observing the ozone layer and noticed that, yeah, we were losing ozone at an alarming rate. And so in the 1980s, 1987 specifically, the nations of the world got together and decided, it's what we need to do is stop producing these things, because clearly we're having an effect on the ozone layer. We're producing CFCs, these are destroying the ozone layer. And then, governments are slow. By about 1991, 4 years later, most of the countries that had signed on to this plan had started to implement mitigation measures. And then this slide, it goes from 1960 to approximately the present day. And what we see is, after mitigation measures had been taken, we don't see as quite a steep drop in ozone amounts. Now, we don't see it rebounding yet, but that's because CFCs tend to have a very long lifetime in the upper atmosphere. But it's encouraging. It's encouraging that we had an effect, and it is also encouraging in that what this has shown us is that here's sorry, I was going to transition nicely into conclusion. I'm rushing forward. I actually have another 10 slides here, which I realize I'm not going to get to, which I actually realized I wasn't going to get to when I was putting this together, but they're still there. So they're still in my head. So let me take a step back and say, all right, so what have we seen? I'm going to try to summarize the observations of Venus that we've talked about here. What sort of a role has Venus played in, all right, I'll be grand enough, in human civilization, as it turns out. This is, well, Venus has helped to show us that the Earth is not the center of the universe. That's pretty significant. It helped to organize, the motivation to observe Venus, especially in the transits in the 18th century, helped to organize what was probably the first successful multinational, non-military collaboration in the Western world, possibly in the whole world. I don't know enough about Eastern Asian history to know if there was more multinational cooperation over there. It helped us to understand the significance of the greenhouse effect. Helps us to understand that that we probably want to consider what we do to our own atmosphere, that there are limits to habitability. It also helped us to identify, and it actually motivated another worldwide effort to improve our living situation by not eliminating, we haven't done that yet, by trying to mitigate the destruction of ozone, which, and I probably don't have to mention this, but just, for the young kids who may not have heard the whole story, the reason we like ozone is because it blocks a lot of the harmful ultraviolet rays. And so if we have too little ozone in the atmosphere, it can cause all sorts of health problems for us. Now, I can make a lot of these similar arguments to study Mars or Titan or Jupiter or or even comets, asteroids, any sorts of objects in the solar system. I don't study those planets myself as thoroughly, and so I'm not the person to make that argument right now. But the key is, this brings us back to how science works. What we're doing is we make observations, we make guesses based on those observations, we make predictions from those guesses, and then we make more observations to see if our guesses are accurate. It's hard to really do this adequately if we don't keep observing, if we don't keep studying objects, we don't keep studying planets, we don't keep studying the Earth. Basically, what we want to do is we want to understand the Earth. We want to understand our own home. We want to understand what's going on here, so that, well, for one, we don't ruin the place, and two, so that we can make the most of our time here. But to do that without studying other planets, without studying the rest of the solar system at the very least, is it's akin to Darwin trying to come up with origin of species and natural selection without ever having left England. How is Darwin going to come up with his theories on evolution if he doesn't go to the Galapagos and see species of mammals that are similar to those that he has seen in Europe, but different enough in such a way that they've adapted to their environment, to their local environment? How does he come up with this theory if he doesn't look at a dozen different species of finch and see how this one seems perfectly adapted to dealing with the vegetation in his or her isolated part of the world, and this one is dealing with a completely different adaptation. So it's basically, I guess that's my pitch. I mean, it's important. We need to be able to compare what we know on Earth to other planets as well, and we're limited. We really are fundamentally limited in what we can learn about Earth if we don't take the opportunity to compare our observations to this wealth of other subjects that we have in the solar system and continue exploring them. So that's the end of my talk. I'm surprised I was as close to 45 minutes as I am, but thank you. If anybody has any questions.